Hello everyone, my name is Kostas. I am a postdoc at the University of Bonn, and starting next year you will find me at Leiden as an Ort Fellow for the next 3 years. So today I will talk to you about my main research interest, which is testing the cosmological principle with galaxy clusters, and we will discuss the findings we obtain when we do these tests. So the main two papers that are related in the following presentations are these ones. So if you are interested in what I have to say, please go and check them. We will start with a theoretical introduction, the necessary one, and the cosmological principle, which, as I'm sure you all know, it's a fundamental pillar of the standard cosmological model, and it states that the universe must be isotropic and homogeneous over sufficiently large scales. Isotropy means that the universe must have the same cosmic properties towards every direction, which boils down to the fact that the universe must have the same expansion rate, the same Hubble constant, towards every direction of the sky. On the other hand, homogeneity means that the universe must hold similar amounts of matter averaged over large cosmic volumes, and this uniformity of the matter distribution means practically that no major bulk flows should take place at large scales. A few words about what bulk flows are. So if we zoom in towards the local scales of our universe, we see that the matter is not completely uniformly distributed. As a result, certain parts of the universe are drawn towards other parts, more massive ones, purely due to gravitational attraction. This creates some local motions of matter throughout the cosmos, which are characterized by their peculiar velocities. When such motions take place for large cosmic volumes, we call them bulk flows. As a result of these motions, when we measure the redshift of objects, clusters, galaxies, etc., that are located within these bulk flow motions, what we actually measure is a combination of two things. Is a combination of the expansion, cosmological expansion redshift, plus a component of this local peculiar motion of clusters that has nothing to do with the cosmological expansion of the universe. As a result, if we ignore the existence of these bulk flows, and we might mistake the measured redshift for the cosmological one, which means we will over or underestimate the true distance of our objects based on the redshift, and this bias then will propagate on the inferred cluster properties that depend on this on the distance of the objects. So the take-home message from that is that bulk flow motions, when ignored, can bias the inferred cluster properties we are measuring. What evidence do we have for the cosmological principle? Well, the main evidence we have comes from the cosmic microwave background, which tells us that the very early universe, and actually the radiation in the very early universe, was highly isotropic within a certain rest frame. The practical assumption that we do in standard cosmology is that we assume that the matter in the late universe has the same rest frame as the radiation in the very early universe. In other words, that clusters, galaxies at low redshifts will behave isotropically within the radiation rest frame of the very early universe. However, this is clearly an assumption, and we need to test it observationally to see if these objects truly behave isotropically or not. When we try to do so, we have discovered that no late universe probe robustly and consistently shows isotropy. So the question is still open. For now, the best approach is to assume isotropy, but nevertheless, we need to test it robustly in order to properly understand the most fundamental assumption we make in standard cosmology. This is where galaxy clusters come in. Let me say a few words about what these exciting systems are. As you know, galaxy clusters contain up to thousands of galaxies, vast amounts of dark matter, and the most interesting component for us, the hot intracluster ionized gas, with temperatures of up to 100 million kelvins. This gas consists of mostly free electrons and protons, and can be detected in both X-rays and microwaves. In X-rays, galaxy clusters are very luminous due to the so-called Bremsstrahlung emission, or free radiation, which produces a plethora of X-ray photons with energies of 0.1 to 10 keV. So what we can do is observe galaxy clusters with our X-ray telescopes, measure their flux, measure their redshift, assume the values of some cosmological parameters, for example, h0, to go from the redshift to the distance, and now we have the distance and the flux, we can derive the X-ray luminosity, which obviously depends on the value we assumed for the Hubble constant, so it's cosmology dependent. In microwaves, galaxy clusters can be detected through the so-called Zunyaev-Zeldovich effect, which is a spectral distortion of the CMB towards the position of galaxy clusters. Now, the amplitude of this spectral distortion traces the thermal state of the intracluster medium gas, of the cluster gas. The total thermal energy, YZ, or in other words, the total integrated Compton parameter, depends on the cluster's physical size. So the bigger the cluster is, the more thermal energy the gas will encompass. So what we can do to calculate the total thermal energy is measure the spectral distortion of the CMB here from Earth, measure the redshift, go from the redshift to the distance through some assumption for h0, measure the cluster's physical size through these cosmological assumptions, and voila, we have the total thermal energy YZ, which is again clearly cosmology dependent. One can measure many things with galaxy clusters, and that's the exciting thing about them. Each cluster can provide us with multiple ways, independent ways to trace cosmology. For example, we can also measure the infrared luminosity of the central biggest galaxy in each cluster, or we can measure the X-ray effective radius of each cluster. Both of these quantities strongly depend on the cosmological assumptions we make. All these cluster properties scale with mass, and as a result, they scale with each other, giving rise to the so-called cluster scaling relations. These are very easy to understand. They are theoretically motivated and have been established observationally for more than 2 decades now. They are usually simple power laws that relate these physical quantities, as you can see in the bottom of your screen, 3 examples. The most important cluster property for testing cosmic isotropy is the X-ray temperature. Why is that? Because we can simply observe a galaxy cluster, extract its spectrum, apply the appropriate thermal emission models, and we can measure the temperature. Now, through this process, cosmology enters nowhere. So the observational determination of the cluster temperature is completely cosmology independent. We can exploit the cluster scaling relations between the cosmology independent temperature and other cosmology dependent cluster properties such as the X-ray luminosity or YZ. Doing so, we have the right part of the equation here without assuming any cosmology. The slope is also completely independent of Hubble constant. And on the left part of the equation, we have a bunch of observables, and the only free parameter practically is the distance, which depends on h0 and the bulk flows that we assume they exist. So we play around with the values of h0 or bulk flows in order to make the left part of the equation match the right part of the equation. Doing so for different sky directions, we can obtain h0 constraints for different sky patches, and then we can simply compare these h0 values and see if h0 seems to be isotropic or not. Let me say a few words about the sample we are using and the 10 scale relations we built for this sample. Our sample is called E-HiFlux. It's homogeneously selected, and it contains roughly the 400 brightest X-ray clusters in the sky, which mostly lie at low redshifts below 0.25. For each of these clusters, we measure the X-ray luminosity, temperature, effective radius, and we measure also using Planck the microwave YZ, and using 2MASS the infrared luminosity of the central biggest galaxy. This allows us to build the 10 scaling relations we can build with these 5 cluster properties, and you can see all of them here in this slide. For each one of these scaling relations, we can extract valuable cosmological information. Here, I will focus only on the most useful ones, which are the luminosity temperature and the YZ temperature relations. So let's move on finally to the cosmological constraints we obtain in this study. First, we will talk about the luminosity temperature relation, which looks something like that, as you can see here. And the question is, will the luminosity temperature relation trace an isotropic h0 or not? to improve our statistics, besides our cluster sample, we use two other completely independent all-sky cluster samples of poorer quality, but nevertheless they help us significantly improve our statistics. Overall, we use 842 clusters, and as you can see, when we scan the sky to constrain H0 towards different directions, what we see is a roughly 10% variation of H0 across the sky, as you can see in this extragalactic map. The anisotropy is detected at the 4 sigma significance. It's very interesting because when we check the direction of the anisotropy found by other completely independent studies using supernova, galaxies, or radio sources, so completely independent cosmological probes, they tend to find a similar direction with us. The only difference is that our detection has a far larger statistical significance due to the high efficiency of our methodology. Nevertheless, we still do not know what is the exact reason behind these anisotropies. It could be 3 things, as we understand. The first one has nothing to do with cosmology. So it could be an excess X-ray absorption from previously undetected gas or dust clouds on top of the absorption we already know of and correct for. So what this means is that maybe some clusters are undergoing some excess X-ray absorption as their photons travel through our galaxy. They appear dimmer to us, and we interpret this dimming as a cosmological effect, while in fact it could be a galactic effect. Not to spoil it for you, but we have done many tests on that scenario, and I can confidently say this is not the case. A second explanation is the existence of a large bulk flow motion that messes up the redshift to distance relation, so the distance-dependent cluster properties, such as the luminosity, or it could be actually an anisotropy in the expansion rate of the universe, at least up to 800 megaparsecs or so, that we can trace on. Now, let's move on to the most useful relation of all, the microwave YZ temperature relation. Why it's the most useful one? Because it's one of the least scattered relations we have, as you can see here, 2 times less scattered than the luminosity temperature relation. And we have roughly 400 clusters for this relation, coming from 2 completely independent cluster samples. But the key here is that the YZ is measured in microwaves, so it's completely insensitive to any galactic absorption. So now we don't have to worry about this extra galactic absorption anymore, since microwave photons are not absorbed by our galaxy. This means 2 things. If we repeat the H0 anisotropy test with the YZ temperature relation, and we do not find the same anisotropies, this would be a very strong hint that the anisotropies we found before have something to do with galactic effects. If we do find the same anisotropies, however, it would point towards a cosmological explanation for these anisotropies. So when we perform this test, we actually find exactly the same anisotropies. I want to highlight here that this map is nearly independent from the previous map you just saw. So again, we find a 4 sigma anisotropy in a dipole form and around 12% spatial variation of H0. To visualize this anisotropy thing a little bit better, we have created the Hubble diagram of these clusters. And as you can see, the clusters coming from the blue region here have a systematically different distance to redshift relation than the clusters coming from the rest of the sky across the whole redshift range that we can trace off. Now, we do the obvious. I have a problem with my presentation. Okay, sorry. So we do the obvious and we stack all the cluster information we have together. So we stack the X-ray, the microwave, and the infrared observations together for each cluster. We combine it with an in-depth exhaustive analysis, and we managed to create the first ever multi-wavelength H0 anisotropy map, which looks something like that. So as you can see, we see a very clear dipole form of an anisotropy, reaching an almost 6 sigma level. This is expected since we have many different independent measurements suggesting the same anisotropy. So combining all together, we reach this very high statistical level. This 6 sigma has been assessed through Monte Carlo simulations. I want to note here that this is by far the most robust detection of a late universe anisotropy ever obtained. However, the question still remains. What if the expansion rate of the universe is isotropic? What would explain our results? The answer to that is a large bulk flow motion. To quantify the scale and amplitude of a bulk flow that would reconcile with our observations, we create the first ever method to constrain bulk flow motions using galaxy cluster scale relations. We use many different scale relations, many different statistical approaches, and many different independent cluster samples, different cosmic spheres and different cosmic cells. Each time we find a consistent, roughly 900 kilometers per second bulk flow motion that seems to extend up to 500 megaparsecs. The exciting thing here is that this motion is completely inconsistent with the expectations from the ΛCDM. So you see that for ΛCDM, for the scales we're tracing, ΛCDM has an upper limit of roughly 200 kilometers per second, while we are reaching 900 kilometers per second. We have went through a very long list of possible systematics that could create these results. I'm not going to bore you with them, but I just list them here, some of them at least. Whatever we could think of and whatever the community has suggested to us, we tested, but we found no explanation for the obtained anisotropies. So for now, at least, it does look like an anisotropy in the local H0 might exist, or alternatively, a large bulk flow motion. Both of these scenarios strongly contradict the standard cosmological model as we know it now. This doesn't mean that one of these scenarios is true. It could mean that we are missing a completely unknown systematics on galaxy cluster scale relations or cluster analysis that we or anyone else have no idea of. However, for now, the most probable scenario is the cosmological explanation. This brings me to my summary. So cosmic isotropy is extremely important not to be continuously tested with new methodologies with high power and efficiency. We create such a method with galaxy cluster scale relations, and we find a more than 5 sigma anisotropy of galaxy clusters in the local universe, which could be explained from a local H0 anisotropy or a large bulk flow motion, or a completely unknown systematic to us up to now. Both of these scenarios, however, strongly contradict the standard cosmological model, and of course, we will keep pushing to improve our data, our statistics, and come up with an answer soon enough. Thank you very much for your attention.